So welcome to the third problem solving session of the Parameterized Algorithms course. So maybe we'll wait for a minute for people to join. Okay, so anyway, we are recording this session, so people may watch this session once we upload the recording to YouTube. So let's begin. So we have completed 3 weeks of this course. So by now you have watched 3 weeks of videos. So week 4 video is out, as well as the assignment is also live. So the assignment of week 3 has a deadline in about a week, and assignment of week 4 has a deadline in about 2 weeks. And the assignment 1 and 2, their solutions are released because the deadline is over. So in this lecture, we will look at the solutions briefly, and the feedback form for week 3 is also out. So I'll encourage you to fill this feedback form. So let's go to the whiteboard and let's first look at the assignment 1 and assignment 2 solutions. Then I will uh, solve some questions, some practice problems, which will help you solve the assignment 3 questions. Okay, so right. So in this week, the videos that we have seen are on this topic called iterative compression, and the problems in week 3 are also from the same topic. And before going to the questions of iterative compression, let's quickly glance through the solutions of assignment 1 and 2. Okay, so this was the first question of assignment 1, and this was a question that was uh, reasonably difficult, and we did not discuss this question before. So let's quickly look at it. So here, let me take the pointer. Right. So you have been given a graph G and a parameter K, and as usual, we are asking the question whether this graph contains a vertex cover of size at most K. So there is this algorithm called crown decomposition algorithm, which we have seen. And in this question, uh, the question is asking that which set of vertices is the crown, and which is the head, and which is the body after the crown decomposition of this graph. So the first step is to find a maximal matching in the graph. In this case, uh, the maximal matching is being shown by these blue edges DE, FG, and PQ. So these endpoints of these maximal matching constitute the set X, and the rest of the vertices, that is the vertices in VG minus X, are forming an independent set. So A, B, C, D are part of the independent set I, and we have this other set X. And now the next step is to uh, find the maximum matching in this bipartite graph formed between I and X. So remember that before we do this step, we have already deleted the matching edges. So these edges are not there. In fact, we have also deleted uh, these other edges. This edge is also deleted. So this we have seen in the algorithm. So anyway, the next step is to decide after finding this maximum matching, which part is the crown, which part is head, and which part is the body. So this has been shown in this self-explanatory diagram. So the head is nothing but S intersection X. Okay, so X is this, all the vertices here, and S is the minimum vertex cover, which we have found by taking one endpoint from each of the matching edges. So here S is these three red vertices C, D, and G. So X contains all these six vertices. So S intersection X is nothing but D and G. Therefore, we can directly get head to be D and G, right? So D and G means uh, in the options, as if you see that only one option has D comma G as the head. So other things you can anyway rule out immediately. But still, for the sake of completion, we will look at how the crown is computed. So, so once the head is decided, the crown is the neighbors along the matching M. So the neighbor of D along the matching is A, and the neighbor of G along the matching is B. Therefore, A and B forms the crown, right? And the rest of the vertices are a part of the body. Okay. I think if you go through the video, then you will be able to appreciate uh, how the crown, head, and body is computed for any graph according to this algorithm. So let's move to the next question. So in this question, uh, we applied some reduction rules, and the question was, after applying these reduction rules, whether the algorithm will say yes or no, whether this instance of vertex cover will be classified as yes instance or a no instance for the parameter value k. So this I think we have seen in detail in the first TA session. So I will not go into details of it, but yeah, we already said that okay, for all possible subsets of A, B, C, D, so there are 2 to the power 4 possible subsets. We will check whether this expression is a vertex cover of size at most 3, and it turns out that one of these subsets of uh, X, I mean A, B, C, D, if you consider this as X, what do they call it? They call it S. Okay. So one of the subsets of S, A, B, C, D, if you consider it to be Y, then this expression is actually a vertex cover. So here there is a self-explanatory diagram. So here, as you can see, Y is taken to be A comma B, and this entire expression evaluates to A, B, and H. And this is a vertex cover for this entire graph, and it has size 3. So we can quickly verify that all the edges are in fact covered by these 3 vertices, A, B, and H. So this turns out to be a yes instance. Okay. All right. So this anyway we had seen in quite detail in the first session. This question we did not discuss during the first session because we did not go till lecture 4. So here the problem was the 3 hitting set problem. And since we have not discussed this before, so let me define formally what is the 3 hitting set problem. Uh, so just give me a moment. Right. So we'll just write down. So in the 3 hitting set problem, the input is as you can see, a universe U. Am I online? I'm just checking if the connection is okay. Yes, I'm able to see the screen. Okay, so input is a universe and a family A. So universe U, a family F of sets over U, and each set in A has size at most 3. So as you can see that every set has size here exactly 3, but at most 3 is sufficient. So each set in A, here the set is denoting is, sorry, uh, they're denoting it as F. So each set in F has a size at most 3, and we have an integer that is part of the input, which is the parameter. This is a parameter, and the question we are asking is that does there exist a set X, which is a subset of the universe, of size at most K, that has non-empty intersection with all the sets in the family? So we are asking in this case that is it possible to pick some two elements, I don't know which two, from U such that all these sets in F are, so to say, hit. Okay. So we apply some reduction rules that we have seen in the lecture. So uh, there are three reduction rules, and finally, in the reduced instance, how many sets are left? That is the question, right? So here is a self-explanatory, detailed solution. We'll just quickly go through it. So here the value of k is 2. So one of the reduction rule was, uh, if you can find k plus 1 sets that contain a common element, then you replace those sets by a set containing that element. So that was reduction rule B. So these three sets in the family contain the element F. So we replace these three sets by a singleton set containing F. And then after this reduction, we have this reduced instance. Here you can see that in the sets, these elements G, H, P, Q, R, S are not present. Therefore, there is no point keeping these elements in the universe because they cannot be part of the hitting set, because they're not hitting any sets at all. So we delete them. So that is the rule RRA, reduction rule A. So after deleting these unnecessary, useless elements from the universe, we're left with this instance. And then again, we are able to find three sets that have common intersection. In this case, these three sets have common intersection A and B. So we'll replace these three sets by a smaller set containing A and B. And then we have this reduced instance. And here the elements in the set are only A, B, and F. So C, D, and E are no use for our purposes. So we'll delete C, D, E. Now we are left with this reduced instance. Here, the universe is only three elements, A, B, and F, and the family contains only two sets. One is A, B, and the other is a singleton set containing F. So, right. So no more reduction rules will apply now. So as you can see, what is the hitting set for this family? Of course, if you choose A or B from this set and A from this set, then that will be a hitting set. But the question is different. The question is, in the reduced instance, after applying all the reduction rules, how many sets are left in the family F? So only two sets. So therefore, the answer is 2. Okay. Is that understood? All right. So this question we had seen in quite detail. So in this question, the question was how many, whether three lines will suffice to cover all the given points. So, and here after applying the reduction rules exhaustively, how many points will be left in the instance? This is a question. So what is the reduction rule? Reduction rule is that if you can find multiple points in a line, you delete those points. So after drawing this line, we delete all these points. So we're left with this instance. So this is the instance. Again, we can draw one line. So we are left with this point only. And k reduces by 1 every time. So this is the final instance. In the final instance, we have only 1 point. So the correct answer here is D, that is 1. I hope that you were able to do this question. This problem, I don't recall whether we looked at it. Yes, so in this question, yeah, I think I defined what was clique. So the question is, in this graph, does there exist a complete graph of size 4, right? Just let me verify if I'm saying the right thing. Right. So whether there is a clique uh, of size k, that is the question we are asking. So we can immediately say that there is no clique of size 4, but whether our algorithm, after applying the reduction rules, will say yes or no, that was the question. So what was the reduction rule? So we looked at the neighborhood of every vertex. So in the neighborhood of A, uh, we have only this one vertex. So this is not a clique of size 3. Again, in the neighborhood of B, we have 3 vertices, and they're not forming a clique of size 3. Similarly, in the neighborhood of C, we have 3 vertices, and they are not forming a clique of size 3. They're not forming a triangle. In the neighborhood of D, there are 3 vertices, but they are not forming a triangle. And in the neighborhood of E, we have only 2 vertices. So there is no question of forming a triangle. Therefore, this instance cannot have a clique of size 4. And therefore, our algorithm will correctly output no. Right? I hope this is clear. If there are no questions, we'll move on to the next one. This one I think I had discussed. So this is a age click cover problem. So there were 2 rules. One rule was to concatenate every isolated edge. So for example, here is an isolated edge. So you concatenate these 2 vertices and you get this vertex, and you delete isolated vertices. So this vertex gets deleted. Endpoints in the edge click cover, what is it? Oh, you contract. So let's look at rule 2 more carefully. What was rule 2? So in edge click cover, they're applying RR2s, and our RR2 says that if G contains an edge UV such that neighborhood of U is equal to the neighborhood of V, then you contract UV and decrease K by 1. Okay, so here the neighborhood of this is only this vertex and this vertex, and the neighborhood of this is also this vertex and this vertex, and we are talking about the uh, closed neighborhood. So the closed neighborhood of this vertex and this vertex is nothing but these 3 points. Therefore, we could contract this edge, and after contracting this edge, we get this vertex. right? So this reduces to this, and if UV is an isolated edge, then you decrease k by 1. So in this case, UV was isolated edge, therefore k became 3. But in this case, UV is not an isolated edge. So after contraction, this point is not isolated. This point is connected. Here, after isolation, this point was not connected. So this was isolated. So here, therefore, k remains same. So k is 3, right? So it's a question I'll check. Yes. Right. Okay. So this was the end of. So finally, how many vertices are left in the reduced instance? That was the question. So 1, 2, 3, 4, 5 vertices are left. Therefore, C is the correct answer. Okay. So now this is the end of week 1 assignments. I think we discussed week 1 assignments in quite detail. So let's quickly look at week 2 assignments. But before that, are there any questions? Okay, I hope that all of you attempted both quiz 1 and quiz 2. I mean, the assignments for uh, week 1 and week 2. Okay, so let me look at this question. So what is it? This is a graph G, and the question is, does this contain a feedback vertex set of size at most 3? So what is the feedback vertex set? Feedback vertex is a subset S of the vertex set. Okay, so such that removal of S from the graph makes the graph cycle free, right? So G minus S has no cycles. So we exhaustively apply. So there were 4 rules, reduction rules that we have seen in the lecture. Uh, the reduced graph after applying these reduction rules has minimum degree at least 3. So as argued in the technical lemma, any k-sized feedback vertex set contains at least one vertex of V3k. So V3k is uh, the vertices having highest degree. I mean, the first 3k vertices when you arrange the vertices in decreasing order of degree. So the question is, in this example, what is the set V3k? Okay, so here is the solution. So degree 1 vertices are removed, that is applying reduction rule 3. So in this graph, we can see there are 4 degree 1 vertices, they get removed. So rule 4 says that if you have a degree 2 vertex, for example, I, then you add an edge joining its 2 neighbors. So J and P are the 2 neighbors of I. You add a edge between J and P. So that's what they have done here. Similarly for H, they have done this reduction and PQ is joined. Similarly for S. So S is adjacent to C and T. So that means this edge was joined, right? Similarly for F. So F was adjacent to C and G. So there is an edge CG in the reduced graph. So this is fine. I'll just bring this here. Okay. So far it looks just simple application of the reduction rules. And then after applying this reduction rules, you sort the vertices of the reduced graph in descending order of their degrees. So this is this set of vertices and their degrees. So D is the vertex with the degree 14, the highest degree vertex. And then this is just simply noting down the degree of the vertices. So what is the value of K? K is 3. So what is the value of 3K? That is 9. So looking at the first 9 uh, entries in this table. So these are corresponding to the vertices having the most degrees, right, in this graph. So our V3K consists of these vertices. So this is nothing but the correct answer is A. DCAKJPQRT. DCAKJPQRT. This is correct. All right. So I hope that you were able to do this question. Let's move to the next question. We'll quickly look at it. So, okay, so this a branching vector was given to us. And if we do branching, and there are 3 branches for every node, and the reduction in the parameter is 2, 2, and 3 in the 3 branches, then the question is, what is the branching number? That means what is that constant to the power k that you will get? So what is that constant? So there, this we have seen in the video, that there is a formula, or that there is a characteristic polynomial uh, solving which gives us the corresponding branching number. It's simply just plugging the values in this characteristic polynomial. So d is the max of these 3 numbers, d1, d2, and d3, and it turns out to be 3. And then you plug in the values of d, d1, d2, and d3 and solve for lambda, and that gives you unique positive root 1 plus root 5 by 2, and therefore that is the corresponding branching number. Okay. So let's move to the next one. Okay, so we have discussed this problem, vertex cover above LP. In fact, in the practice session, I have discussed a problem of exactly similar nature, of similar flavor. So I did not read this question. So let me quickly read this question and then we can look at the solution. So suppose we have the following instance as an intermediate node. Okay, this is an intermediate instance, and the question is whether it has a vertex cover. First of all, we have to know what is the optimal LPOPT. What is the optimal value of what is the optimal LP value for this graph? So we write the corresponding vertex cover instance LP relaxation, and then we solve for it and we find the LPOPT, right? So we have seen that for vertex cover, the optimal LP solution is half integral. That means uh, uh, all the LP values are either 0, half, or 1. So if you set all the variables corresponding to these 6 vertices to half, then you get optimal half integral solution, right? So recall that we check if there is a vertex V such that, okay, so if you delete one vertex and you again compute the LPOPT, which is denoted here by VC star, uh, then you will get a value. You add 1 to this. So you check if this is happening or not, if this equation is true or not. For every vertex, you check. Okay, so for example, here they are removing A. So after removal of A, we are left with this reduced instance. So what will removal of A give us? Anyway, so let's look at the question first. So, okay, so they are saying that removal of A is able to satisfy this equation. But this gives us the following: not all half optimal. So there is another solution where, so here in this solution, all the values are half. In this solution, there is a value of 1 also. So using this solution, they're saying that what reduced instance will be obtained. Okay. And after, okay, that is the first question. So the first question is which reduced instance will be obtained using this solution. Okay. So We start with this graph. So XA is getting value 1. So therefore A is in V1. XB is getting value 0. So B is in V0. And all the other elements C, D, E, F are getting value half. So I'll just copy this thing for ready reference. Ah, how do I copy this? Right, we're able to copy. So this is our solution, which is an LP optimal solution. So all the vertices for which the value is half is going to this set V half. These vertices with value 1 goes to this set V1, and the vertex with value 0 goes to this set V0, right? And then you apply the rules. So you remove V0 V1 and reduce K by the size of V1. So that is, after you remove V0 V1, you are left with only this set and this reduced graph. And what is the size of V1? It is only one vertex is there. So K is reduced from 4 to 3. So this is the vertex you get if somebody gives you this optimal solution. So this is the optimal solution which was given to us, and using this optimal LP solution, you obtained this reduced instance. Okay, so what is the next part? The next part of the question, they're asking the measure. So K is 4 and VC G star is the value of the optimals in the original graph. It drops by how much? So for the original graph, what was the optimal solution? This thing, everybody got half. So, or maybe this thing, both are optimal. So half into 6 vertices, optimal solution is 3 by 2. Here, half into 4 vertices plus 1 vertex with value 1, that is also 3 by 2. Wait. No, sorry. This would be 2, right? Let's look at the quest solution. So how they're solving it. So K changes from 4 to 3. VC star. Oh, sorry. Half into 6 is not 3 by 2, right? This is also optimal. This is also optimal. And the LP optimal value is 3. Either way, in the original graph, in this graph. But in this graph, the final graph that we have obtained, if we write the LP constraints and everything, then the for 4 vertices, the optimal value will be 4 into half, that is 2. So initially K was 4. In the reduced instance, K is 3. So in the original instance, this thing was 4 minus 3, that is 1. The reduced instance, K became 3, the optimal became 2, so that is also 1. So there is no change in this measure, right? So that's what they're saying, that there is no change. So this thing stays the same. So the drop is 0. That is why the correct answer is C. So it's a bit tricky once you are familiar with this LP technique, which we have discussed in the video. Then you'll be able to solve this very easily. There's nothing uh, difficult about it. Okay. So shall we move on? Okay, you can look at the recording later if you have any doubts. Now, no, there's a third part. I haven't seen this third part. So let's see what is the third part. The third part was consider the reduced instance obtained in one. So this is the reduced instance. Okay. Again, we compute the, oh, yes. So again, you compute the half integral solution, optimal solution that turns out to be half for every vertex, so that all, all LPOPT's value is 4 into half, that is 2. Now we check if there is a vertex V in the graph such that uh, this equation holds true. We find that no such vertex exists. So all half is the unique optimal solution for LP vertex coverage for this graph. The two instances obtained as a child nodes upon branching are what? So, so after doing branching, what are the two instances for this reduced instance? That is the question. So you consider any vertex. So they're considering D, each of the vertices have same degree. Consider the vertex D. So if you remove D, then you are essentially covering these edges. So the graph you're left with is D, is this. And because you have already taken D, so your parameter drops by 1. The other branch is not taking D, but taking the neighbors of D. So once you take the neighbors of D and remove D as well as its neighbors, so you're left with a isolated vertex. In fact, yeah, so you remove all the neighbors. Okay, F is also a neighbor of D, so you remove everything, in fact. So you're left with an empty graph, and T is neighbor to all the other vertices. So your parameter drops by 3. So you have K is equal to 0. These two are the graphs you are left with in the two branches. So which one is correct? So this is one branch and this is the other branch. So therefore, the correct answer is A and B. So you are branching on the vertex T. That is given in the question. You branch on the vertex T. Right. So there's one more part to this question. So the measure K minus VC star G drops by how much along the two branches? Okay. So in this branch, what would be the optimal value of the LP? The three vertices half integral solution is give half to every variable corresponding to every vertex. So half into 3 would be the LPOPT. So here LPOPT was 2, to 2 minus VC star. Sorry, LPOPT was 2, K was 3. So we are interested in this quantity. So K is 3, 3 minus 2 is 1. So here K is 2. So this is LPOPT 3 by 2. And K is 2. So 2 minus LPOPT, that turns out to be half. So earlier the measure was 1, now the measure is half. So the drop is half. So first part is definitely half. So we already rule out C and D. So either A or B is true. So what about branch 2? In the second branch, the LPOPT is 0, K is 0. So this measure K minus VC star is 0. The measure in the original graph measure was 1, so 1 minus 0 is 1. So this is 1. So this one is true. Yeah. Are you getting what I'm saying? Okay, so let's move on. Okay, so this is an instance of the odd cycle transversal. So that means that you want to get rid of all the odd cycles so that you have a bipartite graph, and is it possible to remove only one vertex such that all the cycles are destroyed, all the odd cycles are destroyed? So how many odd cycles are there? Three odd cycles are there, and we can see that we can remove A, and that will do the trick. But the question is not that. The question is, in the lecture, we have constructed a graph G tilde, and so to be able to understand this question, you must understand what was discussed in lecture 11. So they constructed a graph G tilde from G, and it has certain properties. The corresponding k-sized OCT, odd cycle transversal of G is what? That is the question. So of course we can trivially say it is A. So you can blindly answer A, but let's see what is the solution. So you'll so I think you can just read the solution. Uh, so first step they're doing, like, computing this quantity. So removing the vertices uh, of Y from the vertex set of uh, G tilde. So we are left with these vertices. Let's just look at this graph. So we are left with these vertices C C1 E1. Just use pencil. C1 E1 G1 B1 D. Oh, sorry, B2 D2. So I'm looking at this B2 D2 and F2 B2 D2 and F2. Fine. So this is a n minus k sized independent set. So k is 1. N is how much? N is 7. Yeah, this is a 6 sized independent set. So as we can see that no two of these 6 vertices are connected by an edge. So this is an independent set. Okay, so now they're doing some algorithm. So we're looking at those vertices of G whose first copy belong to this thing. So I don't have the context of this, so I won't be able to explain what is done here. So maybe we'll park it for next time. But if you have watched this lecture, then you should be able to understand this. But anyway, as you can see, you can anyway identify that, okay, A is that vertex. That is anyway removal of this will lead to deletion of all odd cycles. There are only 3 odd cycles here. So even if I didn't know how to solve this, I would still be able to mark A as the answer, right? So the correct answer is B. But yeah, you should go back and look at how they solved it. Maybe you already know, but I didn't go through the video, so I don't know. Fine, but we'll look at it next time for sure. So consider the following instance of almost two set problem. So again, this is lecture 11, so I don't think I should look at it now. Okay, so now, uh, so how many of you were able to score full marks in assignment 1 and 2? Is there anybody who scored full marks in assignment 1 and 2? Okay, great. So how many of you got 50% or more in assignment 1 and 2? So Shivang has got full marks in assignment 1, it seems. That's good. Congratulations, Shivang. So anyway, so the point is, if you attend these sessions continuously, then and if you look at the video later on, recording later on, I think the questions will not be too difficult for you to solve. So your assignment 3 is due on 16th, I believe. So we'll meet on 18th next. So the plan today is to give you a flavor of how the questions in assignment 3 are. So although by policy I cannot discuss the questions before the deadline is over, so there are some sample questions which we will look at this point. Okay. Make one more page and push this question below. This question below. So I'll let you. So I will let you read the question for a minute. Is the question visible? Thank you, Shiva, for responding. Okay, so you read the question. So there are 4 statements, and these statements are related to iterative compression. So if you've gone through this third week lectures, then you'll be able to answer these questions. So let's start with the first question. I'll take the marker, take the pointer. So the first statement is the following. Iterative compression is typically used for parameterized maximization problems. Is that true? Second question is statement is iterative compression is typically used for parameterized minimization problems. So question is whether you have seen this technique of iterative compression being used for minimization problems or maximization problems. What kind of problems that you have mostly seen in this week? Any thoughts on this? Okay, so what kind of problems have we seen? Okay, so we have seen feedback vertex set, right, in tournaments. So is this a minimization problem or a maximization problem? We have also seen vertex coverage, our favorite problem. So is vertex cover a minimization problem or a maximization problem? All right, so these problems where we are minimizing us, we're willing to find, we're intending to find a subset of the vertex set of the graph, which is as small as possible. We're actually minimizing the number of vertices in the output set, right? So of course, this is true, and the first statement is false, right? We're not using it for maximization problems, are we? No. So typically we are using this technique for parameterized minimization problems. So what is the next question? So if there exists an algorithm solving, so star is any problem. So it's just a wild card. So if there exists an algorithm solving star compression in time, some function in k times n to the constant, then there exists an algorithm solving the original problem star in time order fk times n to the c plus 1. So is that true? So these are true false questions which we have typically seen in the lectures for this week. For example, in the vertex cover alg- uh, algorithm using, uh, in fact, the iterative compression algorithm for vertex cover, we have seen that there is a theorem which says that this is true, that if you have a compression technique that runs in this much time, then you can iteratively do it for n times and you will get a running time of order fk times n to the power c plus 1. So this is actually true. So this implies this, right? So this is true. Okay. So if there is an algorithm, we're looking at the next one. The next one says that if there is an algorithm solving some problem in the disjoint setup. So if you look at the video, so then you will know what it means. So in the iterative compression, sometimes we're interested in finding a solution which is disjoint from the solution that is given to us. So in the iterative compression, we're generally given a solution of size slightly more than our target. So our target is k, we're given a solution of size k plus 1. Then we ask that whether we can get a solution of size k which is disjoint from the given solution. So if there is an algorithm which runs in some function g of k times n to the constant, then there is an algorithm for solving the compression version in this thing time. So summation I from 0 to k is our parameter, k plus 1 choose I, g of k minus I n to the constant. So this is a direct theorem from the book. There is a theorem. So if you look at the book, page number 80, you will be able to see this stated as a theorem. So I would encourage you to read the book as well as watch the videos. So in fact, what I observe is that the videos of the weeks are based on the chapters. So for example, in this week we have seen iterative compression. So iterative compression was discussed in detail in chapter 4. So there is a one-to-one correspondence between the weeks and chapters so far. Okay, so last week we have seen branching. The branching is chapter 3 of the book. And before that, we had seen kernelization. That is chapter 2. So I would encourage you to read the book along with the uh, watching of the videos, then you will be able to solve the questions uh, uh, easily, more easily. Okay, so these two are direct things, so these two are also true. If you want to know why, then you read the corresponding theorems in the books. Okay, so let's move to the next question. So I let you read the question for a while. Okay. So take a minute to read the question, then we'll go into its details. So here we're looking at this joint vertex feedback vertex set. Okay. So okay, so we have been given a certain statements, but before going, we have to decide. That's okay. So we have to decide whether these statements are true or false, and then we have to choose the correct statements. And before that, let's look at what the problem is. So the problem is called the disjoint feedback vertex set problem. Here the input is an undirected graph G, and there is a parameter, integer parameter K. Along with that, there is a feedback vertex set given to you, which is of size K plus 1. That means one more than the size we're interested in. Okay. The objective is what? The objective is to find a feedback vertex set. That means a subset of the vertex set minus S. Okay. So, so what do you want to find? We want to find a feedback vertex set of G of G. G is the given graph of size at most K. Additionally, additionally, we want this feedback vertex set. Let us denote it by X. Just a second. Okay, so we're interested in finding the feedback vertex at X of G of size at most K. Additionally, what do we want? We want such that X is a subset of the vertex set minus S. So S is given to us. So we do not want any overlap with the given feedback vertex set S. Okay, that is why it is called the disjoint feedback vertex set problem. So S is given to you, remember. So S is a feedback vertex set of G of size K plus 1. Right, this is given to you. You are interested in finding a feedback vertex set X of the graph such that it has no overlap with S. Okay. And if such a graph exists, if such a feedback vertex set of size at most K exists, then you return it or you return yes, otherwise you return no. Okay, so now we look at the given graph. So in the given graph, uh, there are 4 vertices in S. These are the vertices in S. So if S is 4, then what is the value of K? So remember that S is the feedback vertex set of G of size at most K plus 1. And here in this example, S has 4 vertices. So what is the value of K? It's an intermediate question I'm asking. So mod S is 4. So it means that K is 3. Because k plus 1 is 4. Mod s is k plus 1, right? Okay, so now let's look at the first statement. It says that S is an feedback vertex set. S is an FBS of size 4 for the graph G. Is that true? So what do you think? You understand the definition of feedback vertex set? The feedback vertex set is a subset of the vertices of the graph whose removal will destroy all the cycles in the graph. So what do you think? So I'll give you a minute or so to give it a thought. So what if we remove S and all the edges incident to S in this graph? So if we remove 1, 2, 3, and 4, and the edges incident to 1, 2, 3, and 4, what will be the graph left to us? What is the remaining graph? What is the reduced graph? How many vertices does it have? So overall, there are 8 vertices. You remove 4 vertices. So how many vertices you are left with? Right. There are 4 vertices, he's saying. Shivang is saying there are 4 vertices you're left with. Now, what are the edges we are left with? So we removed this, and this. And we removed all the edges that are incident uh, to these vertices. So what is the graph we are left with? So how many edges are there in the graph G minus S? What is the size of the edge set of G minus S? 2. That is correct. Shivang is saying that 2 edges are left. So clearly, if we delete all the edges incident to 1, 2, 3, and 4, then we'll be left with edges that are confined within the vertices 5, 6, 7, and 8. Correct. You're right. You're right, Shivang. So these are the edges we'll be left with. So this is the reduced graph after removal of S. So is there any cycle in this graph? So remember that the smallest cycle that you can have is a triangle. A cycle in 3 vertices. That is the smallest cycle you can have. So in this graph, is there a triangle? No, there is no triangle. And in this graph, is there a quadrilateral? That means a cycle of size 4. Because we are looking at a graph with 4 vertices only. So if we have a cycle, we either have a triangle or we have a quadrilateral. So therefore, as we can see, there is no triangle and no quadrilateral. So this graph we can straight away straight away conclude that it is a cycle-free graph. There's no cycle. Yeah. So therefore, removal of these four vertices has resulted in the cycle-free graph, and therefore these four vertices can be considered as a feedback vertex set for the graph G. And what is the size of this feedback vertex set? 4, because there are 4 vertices. Therefore, S is an feedback vertex set. S is an FVS of size 4 for the graph G. Is that true or false? We're just looking at feedback vertices. For now, do not worry about the disjoint feedback vertex set definition. So we're just asking that whether removal of these 4 vertices makes the graph cycle free or not. If yes, then we will say that it is indeed, S is indeed a feedback vertex set of size 4. Yes, so you are convinced. Now you are convinced that yes, this is a feedback vertex set of size 4. So therefore, we will write this at okay. This is a feedback vertex set of size 4. Statement is true. Fine. So let's move to the next statement. Right. So next statement is that S is not an FBS of for G. Is that true? Is that true? So S is not an FBS for G. So it's clearly the negation of what we have already decided about. So for our first statement is saying that it is a feedback vertex set. The negation of that is it is not a feedback vertex set. So immediately we will say that okay, if the first one is true, now how can the second one be true? Because I've already concluded that S is in fact an FBS for G. Okay. Okay, so these two are related. So the next one is saying something interesting. Next one is saying that let me erase these marks. So the next one is saying that if you add one more edge between the vertices 1 and 2, so if you add this edge, okay, we added this edge. This is our edge. Then this instance, now this is an instance of disjoint feedback vertex set. So a disjoint feedback vertex set instance has 3 parameters. I mean, 3 components. So first component is a graph. Second component is a feedback vertex set of size k plus 1, and the third component is k. So the question is, if you add this edge 1, 2, then this instance of feedback vertex set is a no instance of disjoint FBS. So that is the statement, and we have to decide whether this statement is true or false. So if we understood the definition of disjoint vertex set, which we have defined here, then we'll be able to answer this question. So I'll give you a minute to process the statement and uh, come out with a conclusion. So by that time, I will draw the graph that they have suggested. So I'll just push this part to the bottom So this part we know we don't need immediately. So this part will push to the bottom. Okay, so I'm going to draw this new graph that they have suggested. So they're suggesting that you add an edge between 1 and 2. There is already an edge between 2 and 3. And there is a vertex 4. There is also an edge between 1 and 3. And that's all in this side. 5 and 6 are connected. 7 and 8 are connected. What else? And then this edges between S and A. These are the edges. Right. I think I have not missed any of the edges. This is the new graph with 1, 2 being connected. 1, comma 2 is an edge in this graph. So now the question is this instance of disjoint feedback vertex at GS3 a no instance? The first thing is we have identified so we have identified S to be, or rather we are given that S is this set of 4 vertices. So now you are supposed to find, so concentrate on this definition of X. So you are supposed to find an X, which is a subset of the vertex set minus S. So you are supposed to find a subset of this set. So X has to be picked from this set. Okay. This is the overall set of vertices minus S. So you remove S. So this thing is S. So what is V minus S? The rest of the vertices. In our case, V minus S is A. So they're calling it A. That is nothing but A. So from this subset of this set of vertices, you are supposed to pick at most K. Here K is 3. So pick at most 3 vertices from A. That is your job. Such that removal of these vertices will make the graph cycle free. Such that removal of is that possible? If not, then we will say that this is a no instance. So what do you think? Is it possible to pick at most 3 vertices from this set? It's already acyclic. No. So now you have to understand the definition of feedback vertex set. Disjoint feedback vertex. So what is the definition? So we are looking at the definition of disjoint feedback vertex set. Okay. So it says that you are given an instance that consists of a graph. So this is our graph. And it also gives you a feedback vertex set S, but its size is one more than our target. So our target is getting a feedback vertex set of size at most k, but somebody has given you a feedback vertex set of size k plus 1. In this case, value of k is 3. So, right, actually, let me write it down. Oh, it is already, as you can see. So the third parameter is k, right? So see, the instance is in general g comma s comma k. Okay, so here k is 3. Okay, so somebody has given you a vertex feedback vertex set of size 4, and which is that feedback vertex set? This. Now you are asked, you are and you are making this inquiry. You are asked that does there exist a feedback vertex set for the entire graph, not only for g minus s? Does there exist a feedback vertex set for the entire graph of size at most 3, such that this feedback vertex set has been picked from G minus S only? So you are supposed to form this set X of size at most K from G minus S only. So your X is supposed to be a subset of G minus S only. S is given to you. So here S is what? S is this. So you're supposed to find a feedback vertex set from this set for the entire graph. So it should be possible to delete 3 vertices from here such that the entire graph becomes acyclic. Do you understand the difference, Shivang? So you're saying that it is already acyclic, but the graph is not already acyclic, right? Okay. So now do you think that it is possible to find 3 or less vertices from this set such that we can remove them and the entire graph becomes acyclic? Okay. So what are the vertices he will delete? So Shivang is saying that it is possible to remove 3 vertices. So please point out the vertices that you want to delete and I will mark them. 5, 6, and 7. So you're saying that if 5, 6, and 7 are deleted, then the entire graph will become acyclic. So you're saying that, okay, delete 5, 6, and 7. Then once you delete these 3 vertices, all the edges that are incident to 5, 6, and 7 will also be deleted, right? So after the deletion of these edges, do you see any cycle in the remaining graph? Okay, so there is a problem here. So you are able to see the cycle, right? So we have added this edge that is in the question, that you have added this edge. And because of this edge, this cycle, this triangle, the cycle of 3 vertices exists because this triangle is composed of vertices entirely within S. So no matter how many vertices we delete from V minus S, we will not be able to destroy this cycle. Okay. So as you have correctly observed, that is the trick in the question, that they said now you have added this additional edge which has given rise to a cycle which is entirely composed of vertices in S, then there is no way you can delete vertices in V minus S and get a feedback vertex set. Okay. So what is this statement? Is this statement true or false? So what shall we write here? Correct. This statement is true. So It is always a no instance because it is not even possible to delete all the vertices from P minus S. It is not possible to get a disjoint, to get a feedback vertex H which is disjoint from S, because within S itself there is a cycle. Okay, this looks like everybody has understood. By now we have a different question. So now they're asking, now we're looking at the next one. So it's saying either 5 or 6 must go into the solution of the disjoint feedback vertex set for GS, 3. So now you don't have this edge. So now you're looking at the original graph. Let's concentrate on this original graph. So we are looking at this original graph. They are saying that, okay, you have S. You want to compute a feedback vertex set for this graph, which is disjoint from S. You cannot take anything from S. And you want to compute a feedback vertex set of size at most 3. Then you cannot uh, uh, take 7 and 8 only. So both 5 and 7 cannot be, sorry, both 5 and 6 cannot be neglected. So either 5 or 6 must go into the feedback vertex set for this graph, which is disjoint from S, right? I'll give you a minute to give it a thought. So if I solve the question, you can just get the ready-made solution, but the crux of the problem solving session is for you to give it a thought and so to develop that thought process so that you can solve the questions in the assignments. So yeah, take a minute. So your objective is to get rid of all the cycles. You want to destroy all the cycles. And for a contradiction, if you do not delete 5 and 6, then are you forced to see a cycle in the graph? So for the sake of contradiction, suppose that there exists a disjoint feedback vertex set which does not contain 5 and 6. So whatever you delete from G minus S, you won't be able to get rid of at least one cycle. Is that the case? And if that is the case, then which is that cycle which will still remain in the graph? So are you understanding what I'm asking? So I'm asking that if you Do not include 5 and 6 into your feedback vertex set. And you are forced to form the feedback vertex set from this vertex set A only. Then which cycle will definitely not be destroyed? So how about this cycle? So you're not deleting 5 and 6. Even if you delete both 7 and 8 and all the edges, sorry, all the edges incident to 7 and 8, then how about this cycle? This cycle is going to stay there. The cycle is not destroyed. Is that right? Yes. So therefore, either 5 or 6 must be included in the feedback vertex set. Otherwise, so there is no way one can get rid of this cycle. This cycle will remain. So either 5 or 6 must go into the solution of disjoint feedback vertex set for this disjoint feedback vertex set question. So S is this, right? So therefore this statement is true, right? So we'll just say that this is true. Okay. Are there any questions? This is clear, I believe. I'll let you think that in for a few seconds. Okay, thank you for the response. So let's move to the next question. So I'll let you read the question for a minute. So please concentrate on this question, the question number 4. Okay, so we have a third question. Sorry, we have to first read the third question. So 4 is the continuation of the third question. So I'll just push this thing to the next page. So we are looking at the third question. Right. So we may not have time for the fourth question because this question is slightly tricky. But yeah, read it for a minute or so. Okay, so I think you have read the question, so let me go through it. So what is the definition of a split graph? So a graph is called a split graph if its vertex set can be partitioned into two sets C and I, such that C is a clique and I is an independent set. So let me draw a diagram. So let us say that this is a graph. This is a graph. Right. So in this graph, the blue vertices form a clique of size 4 and the pink vertices form an independent set. Right. So let me mark these vertices. So the blue vertices are 1, 2, 3, 4, and the pink vertices are 5, 6, 7. So the vertex set of this graph is this 7 vertices, and it is possible to partition this vertex set into two parts. There are two partitions, 1, 2, 3, 4, and 5, 6, 7. So 5, 6, 7 is an independent set, and 1, 2, 3, 4 is a clique of size 4. So if it is possible to do so for a graph, then such a graph is called a split graph. So you understand why 5, 6, 7 is independent set, right? So there is no edge between 5 and 6 or 5 and 7, or so there is no edge between any two vertices in this set. Do you understand? So do you understand why this graph is a split graph? Okay, thank you for the response. So now in the split vertex deletion problem, so in short called SVD, we are given a graph G and an integer K. The task is to check if one can delete at most K vertices from G to obtain a split graph. So again, we're interested in finding a subset of the vertex set of G. So we're interested in deleting at most K vertices from G. So let us say X is subset of vertex set of G. We're interested in finding an X such that mod X is at most K, and G minus X is a split graph. So we delete these vertices of X from G, and the resulting graph is a split graph. So there is a compression version of this. So this is the SVD problem. This is the SVD problem. This is SVD. SVD stands for split vertex deletion. So let GSK be an instance of compression SVD. So whereas is a set of size k plus 1. So you are given. So what is the instance? So you are given G, comma S, comma K. So S is already given to you, which is uh, a set of at most K vertices such that, oh, sorry. Yes, S is a set of at most K plus 1 vertices such that G minus S is a split graph. So this thing is already given to you that if you delete these vertices in S, then the resulting graph will become a split graph. But unfortunately, the size of S is slightly more than our target. In fact, it is equal to S plus 1, K plus 1. The size of S is slightly more than we would like to have. So we have a split graph, but to obtain that split graph, we are deleting K plus 1 vertices, but that is not what we want. So what do we want? We want this. The task is to find a set S dash of at most K vertices such that G minus S dash is a split graph. That's what we want. Okay, so you understand the definition of compression SVD now? So three components, you want to find S dash. So the goal is to find S dash. So you want S dash to have at most K vertices and G minus S dash to be a split graph. In short, I'm writing SG for split graph. Okay, now we have been given certain statements and we have to decide whether these statements are true or false. We'll number them So you read the first statement. So if you have any questions on the definition of the compression SVD, then you can ask me. Otherwise, we cannot solve these questions. So how do you approach the first statement? So the first statement says, for any split graph on n vertices, there is always exactly one split partition into C and I, such that C is a clique and I is an. So there is only one way. There is a unique way. There is exactly one way to split the vertices into two sets, such that one set is a clique and the other set is an independent set. So what do you think about it? Is it possible to split only in one way, or multiple different splits are possible? That is a question. Okay, so I'll give you an example. Let's do one thing. I'll push these things slightly below so that we have the question in our view. So consider this graph. Okay. So is this a split graph? What do you think? Yes, it is a split graph. So which part is the clique and which part is the independent set? So I want to write two sets. So I want to write two sets, one for C and the other for I. So do you want to give it a try? Which part is a clique and which part is the independent set? Two ways are possible. That is true. So one way is you have 1, 2. So this is a clique of size 2, and you have this independent set. That is one way to partition. The other way is consider this edge as the clique of size 2, and this is the independent set. So you are right, Shivang. So this is one way to split. Let's say this is C1, I1. The other way to split is consider 2, 3 as the clique, and the other vertex is the independent. Some people can also write another partition. They say that okay, 2 is itself a clique of size 1, and 1 and 3 are independent set, is an independent set because there is no edge between one of them. Some people write it, but anyway, point is that statement that only one way to split is not true. So we'll say that this is not true. So this is false. Okay, so how about the second question? For any split graph on n vertices, there are at most n plus 1 many split partitions C and I, such that C is a clique and I is an independent set. So do you understand the question? So I will give you 30 seconds to think about this question. Okay, so let's move on. So let's spend some time on this statement. So I'll do one thing. I'll copy this part. Uh, we'll go to the next page. I'll only focus on this statement. Okay. So here is our statement. This is it for any split graph. J on n vertices, there are at most n plus 1 many split partitions C and I, such that C is a clique and I is an independent set. So let me draw a graph for you. So let us say how about no, this is not going to work. Maybe so this is a clique. This is a maximum clique in this graph, which has size 3. So this is a K3. This is actually a K3. But the rest of the vertices, we have to make sure that they're independent. So this is not a split graph. So how do we make it a split graph? So the other component cannot be there. Okay, so this is trickier than I thought. I thought I have got this. This seems slightly trickier. So let's park it for next time. And you can give it a thought. So let's move to the next question. In fact, we have only 10 minutes left. So we'll probably not go to question 4 and we'll just look at question 3, last 3 statements only. So okay, so I think we have enough space. We'll just push this thing to the bottom. Okay. And here we'll write. So we are going to focus on this third statement now. So this is saying that if you have an ordering of the vertices, so you're looking at the first I vertices of the graph and you consider only this first I vertices and you call it, let us say Vi. So capital P sub I is the set of the first I vertices, and the graph induced on the vertex set V sub I is called G sub I. Okay, so this is the graph induced on these I vertices. Then Vk plus 1 is a set of size k plus 1 such that if you delete from Gk minus 3 these vertices, then that is a split graph. What does this mean? So maybe I'll just make some space first. Right. So you had induced this graph Gk plus 3, which is nothing but the induced graph on the first k plus 3 vertices. Then you removed the first k plus 1 vertices. So what you are left with is a graph. So you removed the first k plus 1 vertices here removed. So what are you left with? So you're left with only two vertices. Maybe vertex k plus 2 and vertex k plus 3. Right? And because you have removed these k plus 1 vertices, so all the edges incident to this first k plus 1 vertices are also removed. So all the edges that are left are between vk plus 2 and vk plus 3 only, right? So trivially, this is if we believe that there are no multiple edges, then this is a peak in two vertices. This is a k2, right? So we can trivially call it a split graph. That's what I think. This is probably true. The next question is similar. It is saying that if you have pk plus 1 as a set of k plus 1 vertices, okay, so it's saying that there exists a set of k plus 1 vertices vk plus 1 such that if you remove these vertices from gk plus 2, then you have a split graph. Okay, so what does this mean? So probably it means that no, by definition, vk plus 1 is the set of the first I plus k plus 1 vertices in the ordering. So there is an ordering which has been fixed. So trivially, what I can see is that gk plus 2 minus vk plus, let's make it minus vk plus 1 is nothing but only one vertex, right? That is the k plus 2th vertex. So this is capital V, this is small v. So if that is the case, it is trivially a split graph because only one vertex left. But I'm not too sure why they're asking the framing the statement like this. Really, it looks true to me. But I'll get back to you if I think that there is a different interpretation of this statement. But right now it thinks I think it seems that trivially it is true. So let's look at the last question. We have only a few minutes. The last question is if S is a solution of size at most K for GI. Okay, when it is saying a solution, so it is looking at the compression. So it is looking at the split vertex division problem. So when if S is a solution of size at most K for GI, that means when you are looking at GI, that is the graph induced on the first I vertices, and if there is a set of K vertices, whose deletion makes the graph a split graph, then S union Vi plus 1 may not be a solution of size at most K plus 1 for the graph Gi plus 1. So what does that mean? So let's just spend a few minutes on this. Okay, so I'll just make some space and write here. Okay, so now you're saying that so are there any questions? Let me check the chat box. Statement is true. For which statement you had said this, Shivang? I don't know. I did not see your message. Uh, Third, okay. Yeah, it seems true to me as well. So let's look at the fifth statement. Okay. So it is saying that if you consider from the entire graph, you consider the first I vertices. So this is GI, this is the entire graph G, and there is a solution of size at most. So let us say this is the solution. Okay, so there is a solution. So this is the set inside of GI. So size at most K, whose deletion makes the graph GI a split graph. Then with this solution, if you also add Vi plus 1, I think there is a typo here. It should be Vi plus 1. So plus 1 is supposed to be in the subscript. Otherwise, it does not make sense. So suppose this is in the transcript. So this is Vi plus 1. So this solution S along with Vi plus 1 is not a solution of size at most K plus 1 for the graph Gi plus 1. So what is Gi plus 1? It is nothing but Gi union this I plus 1 at vertex, right? So for this graph, this thing is not a solution. That's what they're saying. But since S is a solution for GI, since S is a solution for GI, that means removal of S from GI makes the remaining graph a split graph. Then how can it be possible that the removal of S along with Vi plus 1 won't make the graph Gi plus 1 split graph? That is not possible, right? Because S itself is killing all the cycles in GI. Now, if you add Vi plus 1, maybe some more cycles are added because of the addition of Vi plus 1. Now, if you already delete Vi plus 1 along with this, you are essentially destroying all the cycles in Gi plus 1 also. So it is never possible that the statement is true. This statement is definitely false because they're saying that this may not be a solution of size at most K plus 1, but this is in fact definitely a solution of size K plus 1 for the graph Gi plus 1. Do you see that? Yes, thank you. So therefore, this one we can mark it true. So these two things seems trivial to me, but I'll look at it further. But anyway, thanks for sort of. Oh, we had one more question. Fourth question, we look at it. So I just let you stare at it for a minute or so, but we will not take this question today. So this is based on the previous question only. So I will hit the stop recording button, but before that, if there are any questions, you can ask me. Okay, then I am going to conclude today. Thank you for joining.